Good evening, my dear friends. Today I will be doing FEA analysis on a simple cantilever beam in SolidWorks. I will be showing you how to do this FEA analysis. So let's open the SolidWorks. I have SolidWorks 2024 version. Let's say create a part DN. You have to go to the part DN. Let's change the unit to millimeter. Let's first save the file. It's better to save the file always in first time to prevent from any design loss. So we have to save the file here. And so we will be creating the sketch of the cantilever beam in 2D first on the front plane. So the cantilever beam in 2D will be looking like a rectangular plate, right? So I have taken the center rectangle command. Let's assign some value. Let's consider the length of this cantilever beam to be 600 mm and the width let be 150 mm. Okay, that's fine. We have assigned the units and dimensions. Now we have to extrude it into 3D direction. So let's give it some 50 mm in 3D direction. So this is our cantilever beam. Okay, we have to fix it from one side, and on this we have to do the simulation. Let's first save it, and now we have to go to the simulation part. New study. The FEA analysis will be conducted under static simulation because here there is no consideration of time factor. Time is 0. So static simulation will be conducted for this FEA simulation. If there will be time factor consideration, then we have to go with transient simulation. But it is not the case here. We are going with static simulation case. So we have to first apply the material of this cantilever beam. Let's apply it aluminum alloy something. Let's apply it 606 6063 T6 aluminum alloy. I think the properties are visible here. You can drag and see all the properties like elastic modulus, Poisson's ratio, shear modulus, mass density. DC elastic modulus is 69 gigapascal, so it is well enough to handle some good amount of force acting on it. Poisson's ratio is also 0.33, and the shear modulus is around 25.8 gigapascal, so it's less than elastic modulus, but the shear modulus is also showing that it's capable of holding some shear forces acting on it. So let's go with this material. Now we have to apply fixed part of the geometry. So let's fix this part, one face of the, let's fix this face of the part. We have fixed it. See, this sign shows that this face of the cantilever beam is made as fixed. Okay. Now we have to apply the external force. Let's here we'll be applying the external force, but The direction is wrong, it's acting like compressive force, but we will be putting as a tensile force that will be in a downward direction, that is negative z direction. So we have to assign the components based force. Okay, let's z direction, right? So we have to apply that 1000 Newton force, that too in the reverse direction. Select a reference plane or flat face or straight edge, right? It's asking for some reference plane. See, it's a reverse direction, it's acting in upward direction. We have to do it in downward direction. So we have to uncheck this reverse direction part. So now see this force is acting in a downward direction, okay? And this will be something like tensile force acting in the downward, sorry, bending force acting in the downward direction. It will be giving a bending moment to the cantilever beam, and it is like a load acting on full surface area of the cantilever beam. So you can also tell this is a uniformly distributed load, that is a UDL load. Now the next part will be the meshing. So you have to click on the create mesh. So let's create a fine mesh, maximum fine mesh. Maximum fine because a good meshing will always be leading to a good result. So we have to try to keep the mesh as much fine as possible, so the meshing results, meshing and simulation results will be accurate as much. So let's do this meshing part. Say a fine tetrahedral mesh is also created on this cantilever beam. Now we have to do this simulation. See, here we have to click the run the simulation. See, the simulation is now running. See, here we can see the bond misses trace, right? Bond misses trace. Now we want the unit to be in megapascal, so let's do it in megapascal. So you can see the maximum bond misses trace in this lesion chart is 10.47 megapascal, and minimum is 0.0155, which is really negligible. So you can always say that maximum stress will be always acting near to the fixed support part, and minimum stress will be always acting towards the force acting part, because stress will be always acting on the fixed support region, because the body will tend to fracture or fail from that region. So you can see the same result has occurred on a cantilever beam. At the fixed support part, here is the maximum stress. That red region you can see, this red part is a bond. Here the maximum stress will be generated, some bond missile stress, and here the force is acting. Here the blue region is the minimum bond missile stress. Similarly, we will be going with displacement. Now displacement is just opposite of the stress. The part of the body which will be facing with maximum stress, in this deformation will be minimum. So here you can see the deformation is minimum, and here where the part will be experiencing minimum stress will having the maximum deformation. So same thing you can see here. And similarly, we can also see the strain. The maximum strain will be near to the fixed support, and it is around something 1.14 e to the power minus 4. Now let's see how the stress will be behaving, deformation will be behaving. For this we have to go to animate. So let animate it. See how this deformation will be occurring within the body. If you can see, let's do it slow motion. It will be better for you to understand. Okay. Similarly, we can also simulate and animate the stress contours. So see here the stress will be forming on the body. It will be ultimately leading to the fracture of the body. Okay. Now suppose we have to find out a factor of the safety. So how to do that? Let's find it. Yes, define factor of safety plot. Automatic. Let's do it. See here the red reason you can see the factor of safety is something 20.53. 20.53. So here the maximum factor of safety we can consider as 20.53. So ultimately goal will be our goal will be to reduce this factor of safety, because somewhat factor of safety are less than 6 and greater than 2 or 1.5 is a good option to consider for any design. Now let us suppose we have to generate the report of this simulation we have done. So let's click on this report. In this report, we'll be finding from start to end what we have done, like design, missing, boundary conditions applying, and everything into simulations results. Everything will be shown in this report. It's a feature of the SolidWorks that it gives and provides full report, generated report with all the things we have done in the simulations, including all the detailed features like missing number of cells in the missing and its weight, material application, everything what we have done in this SolidWorks till now will be developed in this report. So let's select the A4 size paper. Uh, Here, if you are working in some company, then you can write some designer name. Like here, we will be writing some name, Tosh. Here you can write address, logo, website, URL, something, font, facts, anything you want. You can write as per your company standards or college standards. So let's reports path will be selecting it back here. And what will the document name? Cantilever being. Let's apply, and now we'll be publishing the report. See, the SolidWorks is automatically writing this report for me. It's a very good feature. It shortens our time to very much extent. It's a very good feature of SolidWorks, and it's like a boon of the SolidWorks, which helps us. Helps to directly generate a report in the MS Word form or PDF form, whichever I wish to do it. And see, the report is automatically open for us. Here, the SolidWorks model which we have created is shown. See here what boundary conditions we have applied. This one is about here the mass. See, mass is already dependent on volume and density. The density of that aluminum alloy is fixed, and volume is dependent on the design that you already know. So the mass is calculated by density into volume. That mass is evaluated as 12.15 kg, and weight, mass into gravitation to 119.07 Newton, because gravitational force will be 9.81 gram per meter square. Gram per second square. See what the resultant forces we have applied. That 1000 Newton is broken down in every three directions, x, y, and z direction. So it's like a breaking of the forces in three directions, and finding out the resultant force is also something 1000.02 direction, 02 Newton. So you can see in x and y direction is very negligible forces, but actual forces are only acting in z direction. See here the mesh quality information is given. Jacobian points of high quality meshing 16 point, number of nodes, number of elements. You may wish to increase the number of elements, then you have to reduce the element size. And like for grid independence test, you can do these things. Here cantilever beam meshing is shown, that meshing image which we have developed after meshing operation. See here the form is a stress. Here the maximum, minimum, every information about the result is shown. See resultant stress is very well described in form of table. Factor of safety, and here any conclusion. As you can see, it's a ready-made report. If you wish to add any write-up or something like that, then you can also add in it. So I think it's a very good feature of the SolidWorks. We can use it. Here the designer name is Roche, which we have already seen. We have to put in the during creation of report. Here the date and everything is mentioned. Table of content. Everything is fully formatted. Everything will be done in a very good way. It's a very good feature of SolidWorks. Thank you. Liked my videos and please like and subscribe. Thank you very much.